Okay, hi. Today I'd like to show you a simple tutorial how you can basically implement your numerical integration methods, uh, say using more advanced features of C++. Okay, so the numerical integration rule I'm going to implement this time is so-called trapezoidal rule. Which means that the integral will be somehow approximated by the sum of trapezoids. Okay. Well, what this tutorial today shows you, well, we firstly will go through what the trapezoidal rule is about. Then we will go to C++ to implement, to define the class that will perform the operations. However, the class must be universal. Well, what that means is that we can apply the integration rule to any function we choose. Okay, and as I said before, we are going to use something more sophisticated, some more sophisticated tools that are already inbuilt in C++. Okay. This is more related to the C++ implementation, but firstly, let me just briefly show you what the numerical integration using this rule, this trapezoidal rule, is about. Okay, so assume that we have some function. Okay, we have function f. This is the function, this line f of x. Okay, and we are going to integrate it from a to b. These are the bounds, the lower bound and the upper bounds. Well, I've already said that we are going to approximate the area under the curve by trapezoids. Those are these elements, okay, under the curve, and we basically have to chop the integration region A to B into several integration intervals. Okay, interval x0 to x1, x1 to x2, x2, x3, and so on and so on. And also assume that they are equally spaced. Okay, this is not what you can see over here, but assume that they are equally spaced. Well, if we want to approximate the area under the curve using these trapezoids, we have to know how to calculate the surface of the trapezoid. Okay, the surface of the trapezoid is, say, S is equal to, in this case of the first one, it will be f at x1 minus or plus f x0. It could be actually like that. Where are the brackets over here? Times, or it's times sign over here, x1 minus x2 times 1/2. Okay, so this will actually give me the area over here. Okay, this is something that you should already know from elementary math. curses. And as you can see, we will apply using this method, we will get surface of the first one, okay? And likewise, we get surface of the second one, which will be here, here, and so on and so on, and then we sum them together, okay, to get the area under the curve, okay? So I hope you get the notion of what is it about. So now assume that we have lower bound and upper bound. Low bound equal to A and upper bound equal to B. We have some function f of x, and the trapezoidal rule says that if we sum these trapezoids together, we get the following approximation. Integral of A to B of function f of x dx is approximately equal to b minus a times 2n times f evaluated at x0 plus 2, this is important, 2f evaluated at x1 plus 2 f evaluated at x3, x2, sorry, and so on, plus 2 f evaluated at shouldn't be like that, of course, x n minus 1 plus f of x n. Okay, this should be n. We have n intervals. Okay. So what numbers and to what inputs do we choose? Well, we choose the lower bound, the upper bound, the number of intervals, which will give us actually the precision, because however, if you can see this, this means that the higher number of intervals you have, the better you get the precision, because imagine that this trapezoid is only of this length and you get another one over here, and so you almost perfectly cover this area, okay? So we choose the number of intervals, and that's basically it. And so you get formula like this. However, in C++, you can see that there should be something like loop over here, that for every x defined over here, we calculate the value of the function, and then we set up the coefficients and sum it up together, okay? And well, the algorithm we will develop will be something of this sense, but I will show you how to deal with the coefficients. Okay, so that's basically it, and let's go to C++. So I'm in my Visual Studio. I'm setting the new project, okay, like that. Okay, so I'll close this start page. Okay, I hope you can see the whole environment. Yeah, should be fine. Okay, and as usual I'll add some main file, say main, then I'll have some header and some body file. Okay, so I can now turn back to the instructions I have here. This is related to C++, so let's go through that. We firstly define the function that is supposed to be integrated. Well, before I do that, I just define as usual int main something, and the end return 0. And over here I can set up some function. Say the function will return double. The function is called fun, and the function takes just one argument. It will be double x and will be const. Why I'm setting up the argument like this? Well, what it basically means is that we are passing a reference to some number x, and we are not going to change the value of x within the function. Okay, this is the fastest possible implementation of passing the argument. Okay, because you are telling C++ that you are not going to change x within the loop, and you are passing by reference, so you are not allocating any new space in memory. Okay, and say the function will just return x times x or x squared. This is not that important. We can define whichever function we want. I want to show you how you can integrate something more demanding, such as the density of normal distribution, because this can only be computed using this integration method, this numerical integration. Okay, so let's compile it. Okay, everything works fine, no problem. And what we have here, so we have defined the function. Okay, so now we are going to go to the .h file, and I define a class which is called class Numerical Integration with public area and private area. Okay, public area can be touched from outside of the function. Private area can only be touched by internal methods, the member functions of this class. Okay, so this area is said to be more safe. So here we define the constructor numerical integration, and as a parameter we are going to pass the number of the intervals. Okay, this is really something that is of our interest, and we want to use the number of intervals for any function we will be using. So this is some kind of fixed parameter. Okay, So it will be const reference to integer number of intervals. Okay, let's go to CPP file. Here, for security reasons, we type, safe reasons, we type pragma once, and likewise over here. Here we include the header file, just like that, so that the body CPP file can see the class definition over here, and we implement the constructor. We also define a variable that will hold this information, which will be integer number of intervals with the same name. So what we are going to tell the constructor, we want to tell the constructor, save this parameter into this variable which has the same name, so we have to use this operator, this number of intervals stores the value of the parameter. Okay, should be that. And we also want to include the reference to the header in the main file, so that the main file can see what's actually happening in the class. Okay, so this is the basic stuff we have here. The class is actually not doing anything at all so far, it just stores the parameter. Now comes the more demanding task. We are actually going to implement the CPP file. Okay, so we call the method that actually calculates the value of the integral. We call it, say, integrate, and it will return double. So double integrate, and it takes as parameter pointer to function that has one input. Let me explain this later. And there are two more parameters we'll pass. We'll pass the bounds of the integration. Don't forget that we have this as parameter. Okay. Const double bound const double up bound. Okay, so I hope I haven't made a mistake, but let's see. I copy this definition, and over here I type double numerical integration. Okay, here should be x, doesn't matter, and yeah, okay, so let's take a look at the definition of the integral over here. So as I said before, we are going to do something with a loop. It would be actually easy. We could just calculate the value of the integral of the function for all x, but the problem is that we have 1 over here, 2 over here, 2 over here, and everywhere else but the final element. Okay, so we have 1, 2, 2, 2, 2, 2, 2, 2, 1. Okay, we can use definition by vector, so the coefficient will be something like 1, 2, 2, 2, 1. Okay, so the method I'm actually proposing is to create a vector of coefficients like that, and then to use a vector of function values that will store value fx0, fx1, just like that, but without the coefficients, and the last element will be this one. And what can I do then is that I can take the dot product, which means that I multiply 1 by this element, 2 by this element, 2 by this element, and 1 by the last element, and I sum that together, so I get this result over here. Okay, and this method I will propose, because however you could create a loop where you say if it is the first loop, which would correspond this this element over here, then multiply by 1, and if it is something else, then multiply by 2, and if it is the last one, then multiply by 1 again. But you can see that it is kind of cumbersome. This one is much better actually. Okay, so let's get started. The most important point is to take a look how many values of x we actually have. Okay, we have n plus 1 values of x. Okay, so because here we have xn, but we are starting from 0. Okay, so there are n plus 1 values of x, n plus 1 function evaluations. Okay, so the dimension of this vector will be n plus 1, and so will be the dimension of this vector. Okay, well, I include vector because we are going to perform vector operations. I also type here using name space std to simplify the notation, and I define here the vector of coefficients. It will be vector of double. It will be named like that, and it will be the dimension of numbers of intervals plus 1, and we pre-allocate the values to 2. Okay, what this actually does, let me show you. Let me call this function. Okay, so I go here, I instantiate the numerical integration say with 100 of intervals. Then I perform num int, say call double, that is equal to num int, and we'll be passing the function fun, and we start to integrate from -5 to +5. Okay, and here we'll return 0 so far. Okay, let me just compile that. I expect there will be some problems as usual. Yeah, taking 3 arguments. Ah, yeah, of course. Let me see. Yeah, we can enter, and now focus on what is going to happen with this vector. Okay, so I expect the dimension to be the size of number of intervals plus 1, and the values that are to be pre-allocated in the vector are to be 2. Okay, so this is exactly what I needed. The dimension is 101 and all the numbers are 2 in the vector. Okay, so how do I cancel the that's over here. Let me shift the panel. Okay, so this is exactly what I want, but notice that the coefficients I need start and end by 1, so I just say vec coefs 0. The first element is indexed by 0, must be 1, and so the last one vec and how do I locate the last element? Well, I take the size of the vector, and the size is 101. Okay, but the index of the last one is 100, so I deduct 1 and it will be also 1. Okay, let me show you. Now see what the vector looks like. So the first one is 1 and the last one indexed by 100 is also 1. This is exactly what I needed, and in the same fashion I'm gonna define the vector of function values, but there I don't need any coefficients. Okay, so the vector double function values will be of the same size, but it does not hold any initial value. It will hold initial value 0 if I define it like that. Okay, so I've pre-allocated the vector that will hold the function values, and now I'm going to implement the loop. So as usual, we start by for integer I is equal to 0, I is less than or less equal to number of intervals. Okay, so this will be our 100. So from 0 to 100, this means that there are 101 iterations or loops. Do I++. Okay, and how do we define our xi because you can see that we are going to evaluate within each iteration the function f and with the argument xi. So double xi is equal to, so we started with the lower bound. Let me put the lower bound over here. We have it as argument over here. So low bound plus I times, and now I need the size of the interval. So the size of the interval double is equal to upper bound minus the lower bound. It's upper bound minus low bound divided by the number of the intervals. Okay, but this is integer. Okay, so I have to recast it to double. Okay, so what is this variable? This variable actually represents this distance. Okay, I take the last value, the first value of x, and I multiply and I chop it into these small intervals of equal size. Okay, times interval size. So in every loop I start with x0, so x0 equals the low bound, okay, times 0 times interval size. x1 should be the starting interval, the starting value of the interval, times I times the interval size. Okay, so x0 starts here, x1 starts, x1 is x0 plus the length of the interval, x2 is x0 plus 2 times the length of the interval, and so on and so on. And double function, I don't need it, I can just use function values. I, this is the vector that holds the function value, is equal to, and now I use the pointer evaluate the pointer at xi. Okay, that should be it. Let's see if it works. I'm kind of doubtful, but let's see. So yes, we want to start from minus 5. Okay, and now we want to enter the function and evaluate it at minus 5. Okay, so we are in the function and we are evaluating the function at minus 5. Okay, and we store the result into the vector. Okay, so this seems to be working nicely. Okay, and what more we can do, or we have to do, is to compute the value of this term. Like I said, it's the dot product of these two vectors, and we are going to use more sophisticated method in C++. We could, however, create a method that loops through the function values and multiplies by the corresponding value of coefficients, and then it sums all together. But there are already inbuilt functions for this in C++. Let me show you. I include what's it called, include numeric, like that. And there is a method called inner product, I think. So let's create some variable, say mult value, like the multiplication of the vectors, and let's use the method inner product. Yeah, that's it. It seems to be quite complicated, but it's basically quite easy. The first two arguments are from where to where are we going to take the values of the first vector. Okay, so we want to take the whole vector, of course. So we take the vector of the coefficients from the beginning, so the begin, this is iterator, till the end, just like that, and we are matching it with the beginning of vector of function values. Okay, we don't need to specify the end here because it's obvious that we are multiplying element wise, so the numbers of elements must be the same in both vectors. And here is at what number we start the sum, so we start summing from 0. Okay, so this multiplication over here will basically give us the value of the terms in the brackets, and to compute the value of the integral we just need this term. Okay, but notice that b minus a divided by n is the size of the interval. Okay, so we just multiply a result of this multiplication with this term and multiply by 1/2 because it's over here, and we got the result. Okay, so return 0.5 times interval size times multiplication value, and this should return the correct number. Okay, there is something internal, so there is no serious error. What I did is just I rebuilt the solution. There was some stupid error in the memory. Okay, so let's try it again. So what it does, it actually creates the vectors, the coefficients, and the vector of function values. Then we compute the size of the interval and evaluate the function. So we fill this vector. Afterwards we sum up the values, we calculate the inner product, we have this number, and we return the result. Okay, and that's basically it. That's the value of the integral. You can define any function over here that you want to pass. Like I said before, I want to pass the normal distribution function, the probability density function, so that I will integrate the normal density. Normal density, you definitely know the plot, so I will just show in Mathematica plot 1 divided by sqrt of 2 times pi. I hope pi is written like this over here, time exponential of minus x squared times a half, and show it from, say, minus 5 to 5. So there is some error for sure. Let me just check it and I'll be back. Yeah, I get here can be pi, but the SQRT must be like that. Yeah, this is we want to compute the value under the curve, which is known to be 1. Okay, show you. Okay, so in here I type 1 divided by sq. I include to get the mathematical functions. 2 times 3.149 I think. I'm sorry if there is an error. Times exponential of minus x squared. I can either write it like that or use the inbuilt function okay. I think it's like that, and if we integrate it between, say, minus 6 to 6, I think we should get 1. Okay, you can see the result, and this is usually the case when you would use numerical integration, because you cannot calculate values of, or the integral of function like that in analytical sense. Okay. However, if you increase the precision, the number of intervals, you would get more accurate answer. But it, however, slows down the computation. And this is the last point I would like to talk about today, the precision. Okay, so if we say the precision and the speed, if we define the precision to be related to 100,000 of intervals, we get for sure quite good result, but with increasing number the algorithm is getting very slow. You can see that it really took some time. Now it definitely will take some time. So you get really good number, but it takes some time, and I like to show you how you can in Visual Studio set up some optimization. So I go to properties. Let me show you again. Here I go to properties. Here I go to C++ general and I choose disabled. Okay. disabled. Optimization, I choose maximize speed, and the last thing is hidden over here as a default. Okay, so you still remember how long it took using that method, but let's see it now. Maybe I should pick the point over here. Maybe I cannot debug it. General debug information. Try this one. Yeah. So now it will compute, and you can see it's much more faster than before. Okay, because before it really took several seconds, but now see. So this is a way how you can increase the speed of your algorithms to set up the optimization of the C++. Okay, so that's pretty all from me today, and subscribe for my channel and visit me again.